Hello guys, I present you my favorite project, the worm, computer simulation. Why simulate an organism? The reason is because it's difficult to see what's going on in the real organism. For example, if you wanted to study what's going on inside your body, how would you do that, right? It's difficult. You'd have to cut it. And then if you cut it, you may die. But seriously, even if you wanted to study, let's say, I don't know, a mouse, how a mouse works, right? You would have to cut this mouse, which is kind of yucky, right? But even if you push through and you do that, it's still difficult to see what's going on there. It will just bleed out. You would put it under a microscope. Let's say you would sedate it. It would be a sleeping mouse. You would put it under a microscope and you would try to see what's going on in the cells of this mouse, right? I don't know if you saw a cell under a microscope. A cell under a microscope, it looks like a blurry blob. You don't really see much. You don't see the mitochondria, you don't see the nucleus, you don't see anything almost, right? There are several reasons. One is that everything is the same color or similar colors inside the cell. So in order to see it, you have to stain it. So this means you would have to add some special coloring agent to the cell that colors different things in differently. And then you would be able to distinguish things. But it's still very difficult because everything is so small. There is a physical limitation. If something is smaller than a wave of light, then you just cannot see it with any microscope, with any light microscope. Of course, you have an option of electron microscope, but then it's still difficult because electrons, they have a lot of energy. So when they hit stuff, they damage it. So by seeing things, you would also change it significantly. So you would already now see different thing that you wanted to see. So that's why we need to simulate an organism, because if we have simulation in the computer, then you can zoom in to anything you want, infinitely far, and you can see anything. So there is no limitation on any limitations anymore. If we can do that, then we can really understand how the organism works. Now, which organism to simulate? Of course, ideally, I would like to simulate a human. But this is unfortunately intractable because average adult human has about 37 trillion cells. So unless I have a supercomputer, which I don't, I cannot simulate that. That's why I'm simulating a worm. And the worm I'm simulating is called C. elegans. This is one of the most studied organisms on Earth. And it has about 900, actually not about, it has exactly 959 cells. It's very interesting because you would expect number of cells to vary from one worm to another, right? But it doesn't. So every normal worm has 959 cells. Even though it's so simple and so small, it still has about 35 to 40% genes that are similar to human. So if I understand how the worm works, I also will know a lot about how humans work. Now, how to simulate the worm? Ideally, of course, I would like to simulate every atom. But unfortunately, it's also intractable because one cell has 150 billion atoms. So that's why I'm simulating cells on the level of organelles and structures. One cell has about 30 types of those, so that I can probably I can simulate that. Now, what's the strategy? The strategy is very simple. So I start with a very simple model, and then I make simple steps, and every step must bring me closer to the goal. If you think about it, it's a little bit like how evolution works. So evolution started with very simple self-replicating organism, and then it was making small changes, and in the end, it got us. So it's definitely working. So that's my strategy. Let me show you what I have so far. So this is my worm solution, and it has a bunch of projects. And let me go through some of them. So there is a project called molecules. This project contains molecules and rules for their interaction. So this is all the small stuff that interacts only if it finds itself close to each other. For example, if we open this complex formation rules, it's a CSV file that defines all the rules. So currently there's just a small number of them, but of course we'll increase them as we go. So for example, if this protein and this protein, they find themselves close to each other, then they have this probability of connecting into this more complex protein. And also there is this probability that this complex protein will dissolve into initial constituents. So these are all local interactions. Then there is a simulation project. Simulation project contains all complicated stuff, like organelles and also global interactions. Like, for example, movement of stuff through the space. Like inside the cell, the cell is filled with a liquid, and inside this liquid, the stuff floats there and back. And the way it floats, I simulate using a grid. So I have a grid that spans the whole space, and I track in which cell of the grid the stuff is currently contained. So currently this grid is 3 by 3 by 3, so quite coarse, but I think in future I'll increase it, of course. Then there is visualization project. It contains all the D3, D12 stuff that I use to visualize the cell, because I need to see what's going on the screen. And then there is a worm project. This project contains everything specific to the worm. Note that simulation and molecules, they don't have any worm specific stuff. So in future I can use exactly the same classes to simulate other organisms. So the worm is the only project that contains worm specific stuff. For example, it knows that C. elegans has 6 chromosomes. So it puts those chromosomes into initial cell, and then I will let this initial cell develop according to generic rules. And this is how it looks like right now. So this is the initial egg that's created by the worm project. And it is just simulated as a sphere that contains liquid. And currently it's spherical, but when the sperm connects to it, then it will start changing shape and then dividing into 2 cells, and then further on it will start developing into the worm. I didn't do any of this yet, so this is the topic for the next episodes. So see you there, guys.